So in lesson 75, we're going to work through this idea of continuity of functions. There's a few theorems in calculus that we study that seem really obvious. They're actually very important to calculus and in proving things, but sometimes we overlook them because they just seem so obvious, and this is one of them. It's called the intermediate value theorem, and it says if f is continuous, so this idea of continuity is important, and we'll talk about this later, but if f is continuous on the closed interval AB, and n is a number between f of a and f of b, so the y values, then there is at least one number in that interval for which f of c, so some value in here, c, that will equal n. So in this case, here's an example to kind of throw some numbers in there. Here's our closed interval. We're going to go from 2 to 8. This is a continuous function on the closed interval. And it says n is a number between f of a and f of b. So here's f of 2, or f of a, and here's f of b. It's saying there's some value in here, c, and if we're looking at some fixed number, 42, so 42 is going to be our n. So there, if we pick 42, which is between those, there will be some place, at least one place on this function where we have a value. Maybe it looks like 7, f of 7, or sorry, we don't want to put f of 7. 7, where f of 7 equals 42, so something like that. We actually used this in the past when thinking through synthetic division. We used an idea of finding roots between two integers. But anyway, it says prove that f of x equals x cubed minus 5x plus 2 has a root between 0 and 1. Well, we know this is a continuous function because it's a polynomial function, so we're aware of that. So it fits the continuous part. And we want to know that there's a root between here. Well, if we can show that one of these is a positive number and one of them is a negative number when we plug them in, then we know there has to be a root in between there, because a root is when you'll get a 0 when f of x is equal to 0. And so if we can get something below 0 and something above 0, this polynomial continuous function will have to pass through 0. So let's plug 0 in. We have 0 minus 0 plus 2, so f of 0 is 2. And f of 1, we get 1 cubed minus 5 times 1 plus 2. And so that's 1 plus 2 is 3 minus 5 is negative 2. And so we just showed that f of 1 is negative 2 and f of 0 is 2. So somewhere between 0 and 1, this graph has to cross through the x-axis, so there has to be a root somewhere in between there. Let's review the definition of continuity at a point. So at a specific point, a function f is continuous at a point c if f exists at c and the left-hand limit of f of x is equal to the right-hand limit, which equals the value that we were just talking about. It exists at c. So the left-hand limit has to equal the right-hand limit, which it has to equal the actual value at c. So it has to be continuous at some value c. It can't be an open circle here and then a closed circle. So if we had some case like this, it has a left-hand limit and it has a right-hand limit, but they're not equal to each other, so that wouldn't work. Also, if you just had something where you had an open circle and then more, left-hand limit equals the right-hand limit but doesn't equal f of c. So here we see it's continuous. The left-hand limit equals the right-hand limit, which equals the actual value at c. The definition of an open interval continuity is the function is continuous on the entire interval AB, which does not include A and B. That's what the parentheses mean. If it is continuous at every point on the interval. So we're not concerned about the actual endpoints. So this is open-ended or open interval continuity. Closed interval continuity, it does need to be continuous at the endpoints. So it's continuous on a closed interval AB if it is continuous at every point between A and B, and if it is defined at both A and B, and if the limit, the right-hand limit at A is equal to f of A, the actual value when you plug A in, and the left-hand limit at B equals f of B, so when you plug in B. So it's just saying these have to be included, they have to be filled in. So here's our A and B. In order for it to be continuous on this closed interval, continuous at all these points, and f of B has to equal the limit as f approaches B from the negative, and f of A has to equal the limit as x approaches A from the positive. So a question to think through. Suppose that a function is defined on the interval 1, 3, and f of 1 equals 1, and f of 3 equals 7. So here's 1 and 3. Just going to make some generic points here. F of 1 is 1. Spacing isn't correct here, but here's f of 3 is 7. And its function is defined on the interval. Does a number c exist? So does there exist a c in here between 1 and 3 so that f of c equals 3? So let's say 3 is right here. So by what we just learned, the intermediate value theorem, does there have to be something here? And I've been talking about this, but actually the answer is no. Because this is missing one important fact. It does not say that this function is continuous. So we could have had a function that looks like this, maybe open circle here, a closed circle there, and then open circle here. It's defined for every value. But it's not continuous. So that continuity is an important part of this for this to work. Now suppose f is a function that is continuous on the closed interval -1 to 3. Which of the following could be the graph? So it's on a closed interval, which means the endpoints matter. These are open, so these aren't even defined at -1 and 3. These are defined at -1 and 3, but this one, the right-hand limit doesn't equal the value. So this is our only option where it's continuous. The right-hand limit equals the value at -1. The left-hand limit equals the value at 3. So D is the choice there. Here's a couple questions, these next two examples, that are interesting to work through. Let f be a piecewise function defined as follows. The function will equal the absolute value of x plus 3 when x is less than 1. And then this generic parabola, ax squared plus bx, when x is greater than or equal to 1. Find the values of a and b so that the function is continuous on the interval -infinity to +infinity. So we want it to be continuous the whole time. Well, this function right here is set. Absolute value of x plus 3, and so it's graphed here, and that's what you would want to do. You would want to graph it for x is less than 1. So there it is, and it's continuous. This is a parabola, but it's not set. It has variables for a and b, so we want this to be continuous. So what we actually want to do is we want to, so this, here's just a sample of this parabola. It really could be anywhere, but we want this parabola to be moved up so it is continuous. We want to be it to meet up with there. So what we need to do is find out values of a and b so that it will equal. The way that we do that, we want to find what value is this. What's the y value when x is equal to 1? So what would this be? Well, this would be, we can look at the graph and see that it would be 4. We also could take in our value here. So think of this as two separate functions right now. Absolute value of x plus 3. We want to know what is this equal to when x is 1. This is the number that matters because absolute value functions are continuous and parabolas are continuous. We just need them to meet at the same place so the entire function is continuous. So what we need to do is we need to plug in 1. And this is how we do all the ones that are set up like this, and we get 4. And so what we need this function to equal 4 when x is 1. So we need the second piece of this, so y equals x squared plus bx. We need this to equal 4 when x is equal to 1. And we basically have our answer here. We have a plus b equals 4. Actually, we don't have the answer, but we have something that helps us get our answer very easily. So it says find values of a and b such that f is continuous on the interval negative infinity to infinity. Again, I want to stress the importance. This is continuous. This is a continuous function. The only point in question is where they're cut off. They have to meet at the same spot. So we found where this one was at 1. It was at 4. And so therefore this one had to equal 4 at 1 also. And so here's a generic answer. A plus b has to equal 4. So you have an infinite number of solutions. You could say, well, a equals 0 and b equals 4. Or we could have a is equal to 1 and b is equal to 3. We could have a is equal to negative 7 and b is equal to 11, because they still add up to equal 4. So there is your answer for that. And we'll see several problems like that as we continue through our text. And the last one, let f be a piecewise function defined as follows. F of x equals this rational function when x does not equal c, and equals 2c when x is equal to c. Now what we know about rational functions is that the denominator can't be equal to 0, and if c were in there, the denominator equal to 0. So c is not part of this domain anyway. Well, what we want to do is we want this function to equal this function when x equals c. That's kind of what we did. We want x squared minus c squared over x minus c. So that's our first part, and I'm going to write this twice, y equals. We want that to equal, put a little sub 1 here just so we know it's the first part of the piece function and the second part. Well, this is more generic because it has a c here, so we can't really plug in. But this one here can be simplified, and that's often what will happen. This top part is a difference of squares, so we know this factors to x plus c times x minus c. And then we have over x minus c, and we see this cancels. So we want to look at this. This function x plus c, although c is still not part of the domain, will these two equal at x equals c. So now if we put c in here, we get c plus c, which is 2c. And so 2c does equal 2c, and so the answer is yes, it is continuous. And what ends up happening is first one is really just a line with a hole in it at c. And then the other, so this is c. this other part actually just fills in this hole. So that's from this part here. And so that's continuity of functions. We saw a couple of different examples, and we learned the indeterminate value theorem, which says if a function is continuous, that's a really important part, that the function has to be continuous on an interval a, b, then there's a number between the two y values, f of a and f of b, that at least one number c that lies between a and b, where f of c will equal n. It's not as easy to understand just to read it, but looking at a graph and talking through it makes a little more sense.